Hello, welcome back to AIT 1001. Today we're on lesson 7, parallel circuits. And in this lesson you're going to be constructing parallel circuits using various components. That's one of the main things you'll be doing when you come to the lab. You'll be building circuits, parallel circuits, where in the last lab you built series circuits. You're going to calculate the total resistance, voltage, and current in a parallel circuit. You'll be doing that in the online work and in the lab. We're going to calculate the total capacitance in a parallel circuit. We won't be doing that in the lab, but the textbook covers it, and you'll be doing it in the online work. You're going to analyze parallel circuits using a digital multimeter. These three are the main things you're going to be doing when you come to the lab. You're going to be constructing the circuits. You're going to be calculating the total resistance, voltage, and current using Ohm's law. And then you're going to analyze the circuit using a digital multimeter to confirm what you calculated using Ohm's law. And that's a skill that's necessary, because if you're troubleshooting the circuit, if you're just reading it with a meter, again, if you don't know what you're supposed to be reading, then you would not be able to troubleshoot that circuit. So that's why we calculate what it's supposed to be, and then we confirm it with the meter to make sure everything's working as it should. In the textbook reading, you're also going to learn how to state a simple rule for calculating the total resistance of equal resistors in parallel. There's a quick little shortcut that it shows you how to make that calculation without actually using the whole parallel resistance formula. And then you're going to be measuring the current flow and voltage drop in a parallel circuit. So this is what you'll be covering in this lesson. And for the purpose of this presentation, I'm going to spend a little time and go over how to calculate the total voltage, current, resistance of a parallel circuit using Ohm's law. And we're going to calculate the total capacitance of a parallel circuit. So I just felt like this needed some more explanation, so this is what we're going to cover in the presentation. So for parallel circuits, this is an example of a parallel circuit. I have an AC power supply here. I've got a selector switch here that's going to turn the power to the circuit, the rest of the circuit off and on. I've got two branches here, or a parallel network, that makes this a parallel circuit. If you remember, in series circuits, we just had a single path for current to flow, like this wasn't here. So that's a series circuit, and since this has got multiple paths for current to flow, that's what makes this a parallel circuit. So as we go through, we need to add some values. So what I have here is the same circuit, and I've added in 48 volt, still AC supply. My R1 is 100 ohms, and my R2 is 500 ohms. And like I said, in this example, we have an AC supply, but when it comes to using Ohm's law, we don't care if it's AC or DC. All we need to know is the values of the voltage and resistors and current. AC or DC doesn't matter with Ohm's law. But just in this example, we have an AC power supply. So what can we determine from this circuit? We can determine the total voltage. We can determine the total resistance. We can determine the total current in this circuit. We can determine the current through R1, and we can determine the current through R2. So if you remember, when we did series circuits, we did the same total voltage, total resistance, total current, but we looked at the voltage across R1 versus the voltage across R2, which in a parallel circuit, the voltage across these two resistors is going to be the same, but the current is going to be different, in contrast to a series circuit where the voltage was different and the current the same. So this is what we're going to determine from the schematic. So to begin, we need to figure out our total voltage, and it's given on our schematic here, so we know that it's 48 volts. So our total voltage equals the supply voltage. So there's no calculation there. We can look at the schematic and determine what our total voltage is. Total resistance is a little different matter. We actually have to do a calculation here, and this formula may look familiar to you. It's the same formula that we use to determine total capacitance of a series circuit. And this is actually the conductance formula versus a resistance formula, but the formula is used to determine the total resistance of a parallel network. And was with the capacitance. It's 1 over total resistance equals 1 over R1 plus 1 over R2 plus 1 over R3 and so on and so forth. Depending on how many different branches you have in your network is how many that you add together. Which in this particular case, we're trying to keep it simple. We only have 2 branches. So what that's going to do is we're just going to use the 1 over R1 plus 1 over R2. Just as a note, when it's the same thing, if you remember when we did capacitance, the units must be the same for all resistors in the circuit. And in this particular case they are. I have a 100 ohm and a 500 ohm. But if this was, say, like a 100k ohm and this was a 500 ohm, they would need to be converted to be in the same unit, whether it be the base unit or the K prefix. It doesn't matter what you use, as long as all the resistors that you're trying to find the total resistance for them, they need to be in the same units. If you have the units off, like had one as K and one as a base unit, in the end you'll come up with the correct digits in your answer, but the decimal point is going to be in the wrong place, which is equally important. So, like I said, in this particular case, my units are the same, so we can proceed with the values that we have. So my formula, so if I plug my values in, total resistance equals 1 over RT equals 1 over 100 plus 1 over 500. So that's the formula I'm going to use to find the total resistance of this parallel network. So carry it forward. If you remember when we did use this formula to find total capacitance in series, again, the book shows you how to stick with fractions and come up with a common denominator and work it out using fractions. In this case, it wouldn't be too terribly difficult because 500 would be an easy common denominator, but it doesn't always work out that easy. Say if this was 147, it might be a little more difficult to find a common denominator to be able to work that out. But that's why I like using fractions. I'll take a decimal or a fraction, convert it to a equivalent decimal, and that's what I use to work this out. And to me, it's a lot easier and a lot fewer steps to find your total resistance. So to convert these decimals, all you do is take 1 divided by 100. It gives me my decimal equivalent. And then here I'll take 1 divided by 500 to find my decimal equivalent. So this becomes 1 over RT equals 0.01 plus 0.002. And I think that's a lot easier than trying to add fractions together. So if I add that together, 1 over RT equals 0.012. So now I have this worked down where I've got what I need to do next is get my total resistance by itself. So just as a simple rule, when you reach this point, just swap the RT and your value over here, and that comes up with what your final formula will be. But essentially what you're doing is you're doing some simple algebra. You're manipulating where the variable is located in the formula. So just real quick, to get my total resistance by itself, since one is being divided by RT, I have to multiply both sides of my equation by RT, and then divide both sides by 0.012 to get RT by itself. But just as a quick shortcut, when you get it to this point, just put RT by itself and put this value here under the 1, and that allows you to finish out the equation. So once I've got to this point, I divide this number into the 1, and I come up with a total resistance of 83.33. So 1 divided by 0.012 comes up to be 83.33 ohms, and that is the total resistance for this parallel network. And you may find it kind of odd that I have a 100 ohm here, 100 ohm resistor here, and a 500 ohm resistor here, but my total resistance is less than my smallest resistor. Well, that's one way to check to make sure your math is somewhat correct, is make sure that that value is smaller than your smallest resistor. That lets you know that at least you're on the right track. But what's happening is if you take this branch out and I had just a 100 ohm resistance here, then my total resistance would be 100 ohms. But by adding in the second branch, I give an additional path to flow beyond the 100 ohms even though this is 500 ohms, it's more than this one, it's giving an additional path. Think about a river flowing through different paths. I have a main path here, and then I've got a branch here and another branch here taking some of the flow that could go here, some of it's going here, so that gives me additional flow and actually less resistance because I've got multiple paths. So that's kind of a roundabout way to tell you that in a parallel circuit, the equivalent total resistance is going to be smaller than your smallest resistor in the network, because you're going to have, like I said, additional paths for current to flow. So far we've determined our total voltage, we've determined our total resistance. So now let's find the total current. So total current is equal to total voltage divided by total resistance. Well, now we know those two values. So if I take my 48 volts and divide it by my total resistance of 83.33 ohms, that comes up to be 0.576 amps, or 576 milliamps. So that's the total current in this circuit. So if I check the current on this leg right here, I would read 576 milliamps. If I tested it down here, I should read 576 milliamps. But that 576 milliamps is actually being shared between the two parallel branches. So I've got multiple paths. So I'm not going to read 576 milliamps here and here. I'm going to read part of it here and part of it here of the total. So now we need to figure out how much of that 576 is going here and how much of it is going here. So to calculate the current through R1, we'll go back and use Ohm's law. We'll take the voltage divided by the resistance. So the voltage, if you follow this through here, there's nothing here to drop the voltage. So I've got 48 volts here and 48 volts here across both resistors in the network. So the voltage is going to be 48 volts. My resistance is 100 ohms. So that tells me, if I plug that in and do my simple Ohm's law, 48 volts divided by 100 ohms gives me 0.48 amps, or 480 milliamps. So of the 576, 480 milliamps is going through the R1 branch. R2, I could do the same thing. I've got 48 volts across R2, and my resistance is 500 ohms. So if I do my Ohm's law calculation, 48 volts divided by 500 ohms comes up to be 0.096 amps, or 96 milliamps through this branch. Excuse me. So if I want to confirm this, I've got 480 volts, or 480 milliamps through R1, 96 milliamps through R2, so that's what's flowing through each of these. Does that equal my total current? And if you add them together, you find that it does. So total current's here, fraction of the current here, fraction of the current here, and then total current again back here on our main branches. So that's basically how you break down a parallel circuit to find the total voltage, current, resistance, and then the resistance and current through each branch. So moving forward, we can look at we'll look at a capacitive circuit in parallel. So here I've got a parallel circuit with two capacitors. I've got a 20 microfarad capacitor here and a 45 microfarad capacitor here. They're in parallel, and I've got an AC 24 volt supply through my selector switch. And so we just simply want to find out what the total capacitance is in this circuit. So the total capacitance for a parallel circuit is just simply a sum of the individual capacitors. So this is going to be the same method you use to determine series resistance. Is going to be the same formula you use to figure out parallel capacitance. So basically, sum of the capacitors, just add these two together. So here's the actual formula: CT equals C1 plus C2 plus C3, or however many you have in parallel. We just simply add them all together. So if we add them together, take our 20 microfarad plus our 45 microfarad, and notice them using the same units, and it comes up to be a total capacitance of 65 microfarad. You just simply add them together when they're in parallel. So that's a parallel resistive load and a parallel capacitive load. That's how you do your calculations. And as always, if you have any questions, please post them on the discussion board. Call me, email me, or stop by my office. Thank you.